Now we are going to move to a different algorithm, and before doing that, we are going to revisit the LP norm, right? So LP norm is the general formula for LP norm is as given here, right? And now if your P is equal to 2, then you get the L2 norm, right? So then you take the squares of the values and then take the square root, right? So that's the L2 norm. And remember when we had introduced Adam, I had said that actually we were using L2 norm there, the exponentially weighted L2 norm there. And that's why I'm revisiting this, because now we are going to see the possibility of using something other than the L2 norm, okay? All of this will become clear soon. So this is the yeah, so we can visualize this. So let's fix the norm. Let's take vectors which have norm 1, right? And now if you try to visualize it, now for L1, the shape looks like this, right? So what does that mean? That for any point on this surface, the norm is going to be 1, right? And you can see that. So this point, for example, here is minus 0.5, sorry, 0.5 comma minus 0.5. Okay, I think something's wrong with this, right? And now if I substitute that in this formula, I'll get the answer as 1, right? So all the points which lie on this square, they all are going to have the norm as 1, right? And now if you look at L2 norm, you would have seen this. Oops. Yeah, so if you look at L2 norm, now all the points lying on this circle would have the norm as 1, and it makes sense, right? Because the equation that you get is the following, right? So I'm saying that x1, I'll not use the mod here because anyways I'm squaring. Okay, let me just write the mod plus x2 square equal to 1, right? You're looking for all points which satisfy this equation, and of course they will lie on a circle, right? So that's the how the norm works. Now what happens is that as you take larger and larger norms, right, greater than 2, 3, 4, 10, 100, then if you have small values of x1, x2, right, then these computations become numerically unstable, right? Because any small value raised to a large value will become very, very small, or the other way around, right? If they're greater than 1, again, if you do 1.1 raised to 100, it will just blow up, right? Not maybe 100, but a slightly higher power than that, it might blow up, right? And then you don't want that, right? So that's why L2 norm is the most preferred norm. But as P keeps increasing and it tends to infinity, then something interesting happens, right? So as P becomes infinity, then the norm just boils down to the max, right? So if you look at L infinity norm, then it's just taking the max of the values that you have, right? So in the vector, you have the values x1, x2 up to xn, and L infinity norm is just the max of this. And then we can quickly prove why that is the case. So if I had, if I wanted to, yeah, so let's see. So I'm talking about x1 raised to p plus x2 raised to p all the way up to x n raised to p, right? And then the 1 by pth root of that, okay? And I want to make a case for why this would be infinity when p, why would this be equal to the max of the values x1, x2, xn if p tends to infinity, right? So if I take limit p tends to infinity, I'll just give you a rough outline of the proof. I'll not do the whole thing. I'll just do the necessary part. Now what I can do is I can take this x1 by p outside, right? And I'm assuming that x1 is the maximum value. Let's assume without loss of generality, we can assume that x1 is the maximum value. So this would become x2 by x1 raised to p and so on, and you will have xn by x1 raised to p and then the 1 by pth root of the whole thing, right? Now as p tends to infinity, what will happen is as each of these quantities is each of these quantities is actually less than 1, right? Because x1 is the largest value. So all the other quantities divided by x1 is going to be a quantity less than 1. So now if you're going to raise this to the power of p, all of and p tends to infinity, then all of these terms will disappear, right? So then you'll just have x1 raised to p and then the pth root of that, which will just be x1. So what you get back is just the maximum element that you had in the vector, right? So that's why LP norm, the L infinity norm, is just like is equivalent to taking the maximum value, and that's all we need to do, right? So that's easy to compute. There is no numerical instability there, right? So that's an interesting result. Okay, so now we understand about LP norms in general, and we understand about L infinity, which is just taking the maximum value, right? Now, what is the point that we are trying to make here, right? So recall the equation of Vt. This was the equation of Vt that we had, and this was, as we had seen, equivalent to doing, right, beta. So what if I just expand this, right? Then what we had seen was you are doing beta 2 raised to at time step t, right? So t minus 1 into delta w0 square plus beta 2 into t minus 2 delta w1 square plus all the way up to 1 minus beta delta wt square, right? So this is what we had seen. So your history Vt is actually, if I just ignore all the betas, right? Let me just ignore all the betas. Then this is just like the L2 norm, right? You're just keeping the history of gradients, and then you're taking the L2 norm of that. It's just the exponentially weighted average L2 norm that you're taking, right? Now the point is, instead of doing that, can we replace this by L infinity norm, and does it have any benefits? Right? That's the thing that we want to check. Okay, yeah. So that's where we are headed. So now if we replace it by max, then what it boils down to is that we're just going to take the max of these quantities, right? And that in turn will just boil down to whatever we had at the previous time step, because you're taking the max, right? So you've already taken the max of these two guys. When you are at time step 2, you had taken the max of these two guys and retained one of those. Then again, whatever was the max that you took at time step 3 and retained one of those, right? So then it just becomes like taking a pairwise max, whatever you had at time step t minus 1, the history, that multiplied by meta, and the max with the next guy, right? So that's all we are doing. Notice that here we are not scaling the gradient by 1 minus beta, right? So that's a change that we have made, right? So then essentially now this becomes the L infinity norm of the history of the gradients, the exponentially weighted L infinity norm that you are taking here. And if you're doing that, let's see what happens. So that's the change we are making, right? We are saying that instead of using the L2 norm for Vt, we can use the L infinity norm, which is just like taking the max. It's also computationally very simple. And let's see if that leads to some benefits, right? And now we don't need to take the square root, because in the L infinity norm, the max value comes out by p raised to 1 by p, right? So you have already taken the pth root and then you have got the max value. So there is no more square root here. Square root is only associated with the L2 norm. But the proof that we saw on the previous slide said that the LP norm is just the max, right? After that, there is no squaring, square root of any of those things, right? So we don't need the square root here. So this is what the Wt plus 1 would be. And we did not do any bias correction for Vt, right? We just took, we are just going to take Vt as it is, because it turns out that the max norm is not susceptible to the initial zero bias as opposed to the exponentially weighted average norm that we have, right? So let's see why that is the case. So this is what happens, right? So now if you have the max norm, so again what will happen is that your M0 is, M minus 1 at initialization is 0, and now in this case at time step 0 I had the value 0.5. So my max norm is going to be the max of these two quantities, right? And then it will end up being 0.5. So I'll start from here, right? And so max is of course more zigzag. It's not as smooth as you had in the L2 norm. It's understandable because you're just moving to the maximum values. And so this is so that's why it's not susceptible to the initial zero bias. So we don't need bias correction when we are using the max norm, right? And you're taking the max between beta times the history that means beta times the max up till time step t minus 1, and then the current value, right? So this history is again decaying exponentially, right? Because every time beta gets multiplied with the history, but the current gradient you're not multiplying by anything. Okay. Okay. So that's the justification for not having bias correction. Okay, now let's see. Now suppose we initialize W0 such that, so now we are trying to see if we have proposed that we'll use the max norm of for Vt instead of using the L2 norm. Now we want to see is there any benefit of doing that, right? So suppose that we initialize W such that the gradient at W0 is high, right? We just did a random initialization and it turns out that your initial gradient was high, right? And now suppose further that the gradients for the subsequent iterations are all 0, right? For a few iterations they are 0. So this is what is pictorially depicted here, right? So you have the gradient along this axis, your initial gradient was high, and then for the next few time steps your gradient is 0, and this could be possible because x is sparse, right? So x is sparse, so you in the next time steps when you're seeing the input, the x is 0, so the gradient is going to be 0. Okay, so this is again a typical situation that you encounter. In fact, this is the situation that we have been arguing about ever since we started the discussion on adaptive learning rates, right? So now ideally we don't want the learning rate to change, right, when the gradient is 0. So now you have looked at an update and your gradient was 0, you are in this time step and your gradient is 0. You don't want to do anything to the learning rate, right? Why do you want to change the learning rate at this time step, right? Because you have not doing anything, you did not get any update. But now in the case of the max value, this is what will happen, right? It will not change, right? Because you're taking since you're using the max, your current gradient is 0, right? So then you're just going to go by the max value so far, and hence the history is not going to change, right? Because this is going to be 0. So that is what happens in the case of max. Now let's see what happens in the case if you were using the L2 norm, right, as we were using earlier. Let's see. So let's look at the example. Now I've just changed the example a bit. Suppose that 50% of the inputs that you see are 0, right? So after every input here, every time step you are seeing every alternate time step you are seeing a 0 input, and hence the gradient is also 0, right? And let's say at the other time steps you are seeing a high gradient. It's just an artificial example constructed to prove a point. So let's just see what the point is. Now ideally we don't want the learning rate to change, as I said, when the gradient is 0 or when the input is 0. So in the case of max, initially you had say V0, at time step V0 you had max of 0 comma the current gradient, so your V0 was 1 and your eta was 1 over 1, so it was 1, right? So eta was I assume that the initial learning rate eta naught is also set to 1, so it will be eta naught divided by Vt, and since Vt is 1, it would also be 1, right? Is this clear? Yeah. So just a minute, I'll just write it down. Remember that eta t is eta naught divided by Vt, right? And I've assumed that eta naught is equal to 1 just for the sake of simplicity. Okay. So now eta t remains 1 in this case, becomes 1 in this case. Now let's see what happens at the next time step. At the next time step, my derivative was 0, right? So my V1 is just 0.999 times my history, right? So that's almost 1. So my effective learning rate again becomes 1 by Vt, which is 1.001. So my effective learning rate has not changed much, right? And same for time step 2. Now the gradient is 1, right? Oops. Yeah. Now the derivative is 1 and my history was 0.999. Sorry, this should have been max of 0.999 multiplied by 0.999 because it is beta times Vt minus 1, but it doesn't matter, the max would anyways have been 1. So my V2 is 1 and my learning rate again becomes 1, right? So my learning rate is not changing, and the same thing will keep repeating, right? The next input is 0. So again, it will be 1.001 and so on, right? So this is what my learning rate is looking like. So remember, on the x-axis, I have, so this +1 you need to do, right? So it was easier to draw it like this. So this is a +1. So this is 1.001, 1.002 and so on, right? So my learning rate only changes from 1 to 1.001, which means it almost remains constant as I am moving across. And that's what I want, right? I don't want the learning rate to change too much for the 0 inputs, right? This is ensuring that, right? Now let's see what would have happened in the case of, I'll just do the full stuff and then we start using the point. Okay. Yeah. So now when I'm using this L2 norm, okay, at time step 0, I get 0.001 and then I use the bias corrected value, and then my initial learning rate at my learning rate at time step 0 is going to be 1. Okay, that is same as what I had earlier. Now at time step 0, when I got the 0 input, now you see that my learning rate is still changing, right? Which should not have happened because I did not do anything at this time step. So why should I change my learning rate? But my learning rate is changing because of this exponentially moving L2 norm average that I'm taking, right? So now it increases the learning rate even though the gradient was 0, and this is what the learning rate profile looks like. It was 1, then at time step 2, for no reason, my input was 0. Still my learning rate became 1.4, right? And then time step 3, it again decreased, but again for a 0 input it increased and so on, right? So it's more, it's still making changes when I have a 0 input, and I don't want that to happen, right? So when you have many sparse features, and if you want the learning rate to kind of not get affected by these sparse features, then Adamax is useful because it's not changing the learning rate too much for such sparse features, right? Whereas Adam is changing. Okay. Okay, so now suppose this is what your gradient profile looks like. So at time step 0, suppose the derivative is this, at time step 1 it's this and so on, right? So there are 100 time steps here and I've just smoothened the curve. So there should have been 100 points and I've just smoothened those drawn a curve through those 100 points, right? So this is what it looks like. And now if I so this is what happens for RMSProp, right? So sorry, earlier, yeah, when we are looking at the case of VT using the average norm, even in RMSProp we use average norm. So I am comparing RMSProp with a version of RMSProp which uses L infinity norm instead of the L2 norm, right? So in the case of RMSProp, the learning rate is continuously increasing in this case, okay? And now let's see what is happening in the case of the max version of RMSProp, right? So the learning rate is increasing more smoothly in this case as opposed to in the case of RMS. Okay, so that brings us to the update rule of this MaxProp, right? Which is the version of RMSProp with the using the max norm for VT as opposed to the L2 norm, and that's it, right? So this is as simple as it gets. You just replace the L2 norm by the max norm. And we can also extend this to Adam and call it Adamax. Right? So Adamax is actually an algorithm that is used in practice, right? So the key idea here was to use the max norm instead of the L2 norm, right? Okay. So this is what the update rule for Adamax would be. So this is Adam. You had the momentum term, you had the bias correction, that will remain the same. Then you had VT, which was L2 norm, and then you had the bias correction. But here you will have MET, which is going to be the max norm, and since it's max norm, you don't need the bias correction, and then you will have the update rule for WT, right? So everything remains the same, it's just the equation of VT that changes, and VT does not need bias correction in Adamax, right? So that's all there is.